So today I'm going to be talking about two topics, both in domains having to do with mathematics, and those are mathematical constants and the Riemann hypothesis. So let me just jump right in. So I'm first going to talk about constants. So while I'm doing that, let me tell you about how constants have been exposed previously through Wolfram alpha. Of course, you're all familiar with control equals and equals equals, those great natural language discovery mechanisms. And historically, in previous versions, you could type in, if you were interested in a mathematical constant that you knew about, you could type in a name and get a lot of good information on it. So for instance, pi here is probably the most famous mathematical constant, and we see all the information that alpha would give you. This is the same as what you'd see on the website. I just happen to have it running in my local session here. But you could also get this within Mathematica, as I said, through equal equal. Just as another example, Catalan is a little bit less familiar of a constant, perhaps, but we get a lot of good information, continued fraction information, alternative representations, ways you can write it in other mathematical forms, series representations, and so on. So constants have been in alpha for quite a while, and so this is nothing new in a sense, but there are some new oh yeah, and let me just quickly wanted to mention a few maybe just interesting cases that you may have not run into, but one of the fun things about constants is they're sort of simple in a way. They're simpler than, say, mathematical functions, which is a topic I talked about last year. There's no complicated analyticity conditions or anything like this, but they tell you, they pop up in interesting ways you find. So for instance, the first example I've got here, Fibonacci's constant, is an analog to, it's the limit of the Fibonacci sequence as the terms go to infinity, where the Fibonacci sequence is similar to Fibonacci, which you're probably all familiar with. However, it takes 3 terms, thus the tri in the name. And interestingly, this sort of constant that arises through a limit of a series actually also comes into play having to do with the length of a side and the geometry of this shape you see here, which is called a truncated icosahedron. There's other interesting from a physical point of view constants. I show here an example of the diamond lattice percolation threshold constant, which says if you have a diamond lattice and you start activating points, what fraction of those points do you have to choose before there is a phase transition where you have a long-range connected set of lattice points. And so this has interest in the physical world, even though the constants I'm talking about at this point are not physical constants. They're all mathematical. You can all derive them with pencil and paper or maybe a computer in some cases. We don't talk about dimensionful constants, for instance, in this domain, but still ones of physical interest do occur. And then there are just some fun ones. This one, Wadsworth constant, refers to the fraction of a YouTube video that you have to skip over to get to the interesting part. And that has empirically been determined to be 3/10. Some people may have other bounds on that constant, but that's what we have. So let me talk about the goals of why are we wanting to change the way constants are treated in alpha. First of all, we want exposure in the Wolfram language in a way where you can get, say, the series representations without having to retype them yourself, without copying and pasting from the Wolfram alpha output. We want to extend the content we've got because Wolfram alpha, when I started working on this domain, had about 240 constants defined in it. At this point, we've got in the pipeline over 500. Right now, in the version I'm going to show you today, we have just about 400 constants exposed, many of which come from a series of sources. Those of you who have interest in mathematical constants, I'm sure are all familiar with many of these. Finch wrote a great book where we've tried to get everything that he's given us. And then things like the OEIS, the Online Encyclopedia of Integer Sequences, and Math World, which is I see Eric sitting here. His baby. We've scraped for some constants there as well. So that's sort of the goals. So let's look at what we've got at the moment. This is the current list of mathematical constants, and just looking through the names, sort of scanning, you can see there's a wide variety of things. There's things like the grazing goat constant, things from Gauss, so things that have been around for a while, all kinds of stuff, and I won't belabor it by trying to read off too many of these, but as I said, we've got about 400 right now, and more in the pipeline that will be exposed before version 11.1. To give you a sense of what kind of data we have for these, I've given a list of the properties. So we can see that there's what we call, so first of all, classes tells you about entity classes, for those of you familiar with the entity framework. Defining formula is like, and I'll kind of follow along with the example I've given below for the Eladi-Grinstead constant. The defining formula tells you sort of how do you write down what this thing is in a closed form, if possible, or as an infinite sum, or whatever form we have, what is it? We've got a numerical approximation, and where possible, what we've tried to do is return 1,000 digits so that there's a fair amount of precision you can get without having to compute yourself. And also in the future, we're going to try and return sort of methods or functions by which you can calculate more digits for certain of these constants where such an algorithm exists, and we can return that for you. There's things like integral representations, limit representations. These are things that if any of you have played around with mathematical function data, you're familiar with. But just to give you some example here, for Eladi-Grinstead, you see what a series representation would look like. It's something that involves an infinite sum or perhaps even a finite sum. But so we have various forms of representations. We have a short numerical approximation. That just is because you may not want to look at these 1,000 digits when you're trying to scan through, say, a table that you've created. So we give a shorter version to 16 digits, which I don't see here for this particular entity, but, oh no, here it is. Here, so obviously this will be a little bit nicer to look at if you're looking through a lot of them. We've got simple continued fraction terms. So here are the first few terms. In this case, looks like about 100 terms we have for the continued fraction representation of Eladi-Grinstead. And then we give a traditional notation and a standard notation so that you can use these perhaps in your session if you want to write a paper or just talk about them in traditional form. You've got something there to use. Okay, here's another example, just showing you Euler's, the base of natural logarithm constant. And here we've got, of course, a lot more data because this is a much more fleshed out constant in the literature. You can see the nice pattern you get with the continued fraction, simple continued fraction of E, to those of you who are familiar with that pattern. So yeah, just giving you an overview sense of what data is here. Now, one sort of very important use case that we wanted to address when we were sort of building this domain is, if someone comes with a number that they're trying to identify, and some of you may have seen David Sotomayor's talk yesterday about a similar topic, but you may want to identify, I've got some physical model or some mathematical computation I've done. I want to know this 12-digit number I've got out, could that be represented by any closed form solution or other well-known number? And so that's why we wanted to build in some discovery mechanisms to allow you to do that sort of thing. So for instance, in 11.1, there's a function called mathematical constant data, and you can see here how it behaves. Now, there's a bunch of different argument structures you can pass here, but for the purposes of what I want to talk about right now, I'm just going to point out that you can submit an interval as the first argument, and it'll return all of the constants that we have knowledge about that are within that interval. So here you see all the constants between 1 and 2. Maybe that's not the most interesting sort of a query, but what if you discovered this great new number 3.1415 and you wanted to know what that might be? You could put in this interval and you discover, well, it's either pi or an approximation for pi, or maybe it's something we've never heard of before, but those are the possibilities that we know about. Okay, and another method for discovering these entities are implicit entity classes. And I'm going to show you the syntax here. Unfortunately, I can't execute this piece of code because I'm right now running Mathematica 10 on my machine, and this is new in 11 and later. So what you see here is sort of the syntax. You can ask for entities that have a certain property, a property in a certain range. So here I've asked for all the mathematical constants between negative infinity and 0, so those would give you all the negative constants, for instance. Oh, and did I show you the entity classes? Oh yeah, I forgot to mention before on this previous slide the entity classes. You can see we've got a large collection of different sets of constants, so another way you could get all of the negative constants is just by querying this entity class negative constants. So, and there's a variety of other collections there that may be of interest. Okay, so that's all I wanted to talk about right now on mathematical constant data, but I would encourage you at the moment, as it's released, to explore if you have an interest. Let us know if there's other constants that you're interested in that you'd like to have data put into the system for. Let us know any suggestions you have would be great, because we want to make this as complete a repository as possible. So before I transition to my next topic, which is the Riemann Hypothesis project, I wanted to take this opportunity to thank the people who are involved besides myself. Of course, there's people like Oleg Marichev and Eric Weisstein, who you're all familiar with, and I don't think they need any more accolades from me, but these interns did a great work this past summer and previous summers collecting. So Albert Tamizan here, he collected information on mathematical constants and functions, and Amita and Arindam here collected the work that I'm about to show you on the Riemann hypothesis. And believe me, their mathematical expertise exceeds mine quite a bit, and I would not have been able to do this work without them. So let's go now to the Riemann hypothesis project. So the goals here are, there's a few of them. First of all, we've tried in the past here at Wolfram several instances of trying to collect pure mathematics, formal mathematics knowledge that is opposed to what people typically use Mathematica for, which would be computational mathematics. How do I do this integral? What is the population of France? That kind of thing, where you're returning numbers or expressions. Here we want to return really just conceptual things built of concepts, if you will. Maybe that's the best way to say it. And we've tried that in various incarnations in the past. There was a project to collect results dealing with continued fractions that we put a lot of work into. There's a theorem formalization project and in general mathematical formalization project that is going to be spoken about in the talk. I think it's immediately following my talk right now, so please stick around for that. It's really interesting work. And another example is work on function spaces, which Eric Weisstein has, oh, and I misspelled your name, I apologize. Eric Weisstein has worked on, and I'm actually not sure when your talk is, Eric, but you can all check this. Okay, there you go. So please go to Eric's talk as well. Another reason we chose this, this topic is because there's a relatively small amount of I'll explain what these are in a minute here, but they're sort of alternative formulations of the Riemann hypothesis, and there may be in the literature on the order of 100. I don't think we've collected them all necessarily. We've collected a large fraction of them, but that's sort of at a number where over the summer we could get our interns and sort of complete the project, or get it 75% of the way completed, so that we can say we have a sort of we have all the knowledge collected about these particular types of entities. And the other interesting thing about it is that unlike some of the other projects, maybe say function space work, which is really interesting and important, but we don't necessarily have a powerful enough language yet to represent everything we'd want to in that type of domain. Whereas, surprisingly, or maybe perhaps not surprisingly, the Riemann hypothesis is sort of simple enough to state that we've got most of the pieces built into the language already. And so that's what made it a good project to tackle in this sort of manner. So let's just look at what data we've collected. We've got right now 46 entities collected over the summer by Arindam and Amita. And you can see there's a variety of names. They're mainly associated with people, who's ever published it in the literature has their name attached to it. Many of these don't have their own name, although we'll talk about one in a minute that does. And what type of properties are we going to be able to look at for these? Well, we've got references. So, if you look at one of these entities, you want to go to the literature, see what paper it was in, you can find that. We've got the dates they were formulated. We've got who formulated them, and that's linking into people data. So you can do entity value of the person that formulated this, find out more information about their biography, perhaps. We've got the relationship to the Riemann hypothesis. So when we collected these, we found that there were a class of these formulations or statements that were equivalent to the Riemann hypothesis, some that are consequences of the Riemann hypothesis, and of course there are some statements that are stronger than the Riemann hypothesis that then imply the Riemann hypothesis. So we wanted to, basically state in a simple way what that relationship was. And so here, and then the most important perhaps is the statement formulation. So you can actually see the formal mathematical expression for what these things state. And I've given an example here. First of all, the Riemann hypothesis itself. So those of you who are unfamiliar, perhaps it's a kind of an esoteric statement if you're not familiar with analytical number theory, but the statement is that all of the non-trivial zeros of the Riemann zeta function, which is a special mathematical function, occur on the line real part equal to a half. Okay, so that may not seem like that interesting of a topic, but of course it's a famous unsolved problem. It's been unsolved for 150 years, and perhaps the reason that it has such interest in the community is because it's related to the distribution of prime numbers. And of course, everyone who's studied mathematics and been sort of fascinated by it at any point in their life has probably thought about prime numbers and been attracted to that. So it's an interesting field of study. So let's look at how the Riemann hypothesis actually works. If you try and formalize it in the Wolfram language, we can see that, so first of all, we wrapped this in a pure function that's merely to, so that some of these symbols, we can give you, you can choose sort of what symbols to put in here. This is following the syntax of Wolfram, mathematical function data. But so what does this say? It says that for all z, where zeta equals 0, there exists an n greater than 0. So basically, this part of the statement is taking care of the trivial zeros. Those are the ones that are at the negative even integers. So it's saying that either there exists an n, which is a negative even integer, such that z is equal to that, or z is equal to 1/2 plus a purely complex part. See, y is real, I times y is an imaginary part, and then you've got the 1/2. So this is exactly the statement that all the non-trivial zeros are on the critical line, real part equal 1/2. So do we have the other version of this statement? So as I said, this is known to be equivalent or actually implies what's known as the prime number theorem. Well, it implies the prime number theorem, but it is also equivalent to a stronger statement called the prime number estimate, which gives some bounds on the, so the prime number theorem says that the number of primes below a certain number approaches this log integral function as the numbers get larger and larger. The prime number estimate just puts, prime number estimate just puts a particular bound on this. So it says how fast those numbers converge. I see I'm running short on time, so I'll try and go quickly through this last bit. Just to give you a sense of the different types of formulations that you might find here, you have ones that involve infinite sums, integrals, integral transforms, limits, derivatives, and often these big O and little o estimates. Those of you who may be familiar with big O and little o notation, these are sort of statements about the asymptotics of various functions, and this is an example where some of these constructs did not occur in the Wolfram language. So what I said earlier is true, that the majority of this can be expressed in the Wolfram language, some of it could not, so we had to invent our own symbols for big O and little o, and those are returned as part of these formulations. I just gave here a grid so you can see all of them laid out, and you can see they're relatively short statements usually. They're things that we can. This is sort of proof of statement that all of this can be expressed within the Wolfram language. And I had a few more things, but I think rather than that, I will just pause here and see if there are any questions.